this presentation. And today I will talk about functional transformations and boundary crossing problems for Brownian motion and Einstein-Univac processes. So this talk will consist of two parts. The first one will be on functional transformations for Brownian motions, and the second part will be for functional transformations for Einstein-Univac processes. So these are based on two papers, one on a set of papers with Pierre Paty and a paper with a recent paper with a student of mine, Aria Ahari, and another colleague, Massimiliano. So let me start with the Brownian motion, and we suppose we are given a Brownian motion Bt on a filtered probability space omega f ftp, started from some point x, which is a real number. Well, most of the time we take this x to be 0. Is everything all right? Yes?
Yes, it's okay, yes.
Yes.
Yeah. And we suppose that f is a real valued function defined on the positive half real line, which is continuous such that f0 is different from x. So we suppose that f0 is different from the starting point of the Brownian motion. And we are interested in the first time, the distribution of the first time when the Brownian motion hits this curve f. So such a problem has applications to special functions, numerical methods, heat equations, sequential analysis, path-dependent options, as well as Rivian problems, default penalty functions in risk theory, and as well as applications to neurology, biology, and physics. Many authors have worked on this, and this is not an exhaustive list, but I could give the name of Bachelier, Levy, Daniel, Strauss, and Farabi, Breiman, Shep, etc. Okay, so some general results on the boundary crossing problems for Brownian motion. The most important one is a result by Strassen, which says that if the curve f is C1, that means continuously differentiable, and here it's defined on R. So this can be a function defined on R or R plus. So if f is continuously differentiable, then the law of Tf is absolutely continuous with a continuous density. There is a result of Kolmogorov, Erdős, Petrovsky as well that says that basically under some regularity condition, namely that 1 over square root Tft is increasing for large T, and f is itself increasing, then the distribution of Tf is diffectious if and only if this integral is finite. And finally, a result of Novikov states that under the condition that f is continuous, f prime is non-negative, f double prime is non-positive, and f prime t over square root t tends to infinity. As t tends to infinity, then we have these asymptotic results for the term of the distribution of Tf.
Sorry. A question, please, Larbi. What do you mean by diffictious density?
What do I mean, sorry, by?
Diffictious density.
Diffictious means that the probability that Tf is finite is less than 1. It's not.
Okay.
Thank you for the question. So the usual methods that are known are Gersanov's approach, which means using a change of probability measure. So we think about the process Bt minus Ft heating 0. So the law of this process is absolutely continuous with martingale measure given as here. So we can use the Dup's optional stopping theorem to find a relationship that relates the distribution of the heating time of F to the distribution of the heating time of 0. So here you have a functional that is complicated to calculate, and somewhat we are just transforming the problem when we do this. And the quantity of interest here that we need to compute is this thing here, which is the expectation of the exponential of the integral from 0 to t of ds, the second derivative of f against ds conditional on t0 equals t. So this is a complicated functional or expectation to calculate. And by using Williams time reversal formula, this quantity amounts just to computing the expectation of the exponential of a functional of the three-dimensional Bessel process, three-dimensional Bessel bridge, sorry, between x and 0. Instead of process here, it should be bridge. So this quantity is still complicated to compute. And so the problem is complicated even for very simple functions f. And but you have methods which allow you to say something interesting for more complicated curves. But the Gesanov's approach works for the quadratic functions. Any questions? Or should I carry on? Okay. So among the other methods, the inverse method of images, and this is an analytical method which amounts to considering this probability, the probability that Tf is larger than T, and at time T you are at X. So this is a space-time harmonic function. It satisfies this equation, which is the heat equation, with the given boundary conditions here on the domain given above and on this domain. So the important condition is that h of ft t equals to 0. So the curve f solves a kind of implicit equation. And so we can infer on the form of h given here by dictating that it's of this form for some measure f, and for some sigma finite measure f, and actually for any sigma finite f measure f, we can prove that there exists one curve small f which satisfies this equation with h given as below. And with that, we can state the following result. So for that particular curve f, which is a root of h of xt equals to 0, we find that the distribution of the heating time of f is given by this integral times dt over square root 2 pi t to the power 3. So the method of images allows to treat many examples, including the straight line, which we obtained by taking the measure to be the delta measure at 2 theta, say, in which case we find that ft is this curve theta plus bt with b given as here. So we can treat the straight line using the method of images. More generally, the curves obtained must satisfy that f is infinitely often differentiable. Ft over t is monotone decreasing, and f is concave. So many functions do not satisfy these conditions, and hence they cannot be treated by the method of images. And so we need other methods to solve these problems. So with Pierre Paty, in 2014, we have published a paper on a functional approach in the Brownian setting. So the idea we use here is that we think about constructing a whole family of curves for which we can solve the problem as soon as we know how to compute the probability density function of the heating time of some curve for some particular function f. So from one function f, we construct a solution to the problem for a whole set of or family of functions. Let us record two important properties of Brownian motion in this context. The first one is the scaling property, or the self-similar property of index 1/2. And the second one is the time inversion property, which says that the second property is the time inversion property. So T B1 over T as a process is again a Brownian motion when B is a Brownian motion. So both properties are satisfied by self-similar macro processes that have the time inversion property. This is one of the question I looked at in the past. So I was interested in characterizing the classes of macro processes having the time inversion property. Now, there's a lot of work done in this direction, but I will not say more about it. And so what I would like to say is that what I will talk about now extends to Bessel processes and Dunkel processes, which have the two properties I just gave above. So the boundary crossing result, which we discovered with Pierre Paty, says the following. So we fix f a continuous function on R plus with f0 different from 0 as before, and we define Tf to be the first time when B hits f. And for beta and alpha real numbers with alpha with alpha positive, we introduce this family of transformations. So S alpha beta of f will be 1 plus alpha beta t divided by alpha f of alpha squared t divided by 1 plus alpha beta t. Well, with f alpha beta given as the image by S alpha beta of f, we have for all t less than zeta alpha beta, the probability distribution of Tf alpha beta and the image of the probability that Tf is in dt by S alpha beta is given by this. S alpha beta is defined only for functions here, but you can extend the definition to absolute continuous measures and other measures and probability measures by first defining this for absolute continuous measures and then extending it readily to an arbitrary probability measure. So if you know the PDF of the, let's say if f is C1, it's continuously differentiable so that Tf, the distribution of Tf has a continuous density with respect to the Lebesgue measure. And if you know the PDF of Tf, of the distribution of Tf, then you can construct the PDF of the first time when you hit f alpha beta, which is a two-parameter family of curves depending on alpha and beta as above. So I will not have time to prove this result, but those interested in this can look at our paper with Pierre Paty. And so as a consequence, we have this result, which is another way to write what I stated above. And examples of images are given here. So the straight line remains stable by this transformation. You obtain again a new straight line. However, the square root boundary changes into the square root of a quadratic polynomial, while the quadratic polynomial changes into a quadratic polynomial divided by a polynomial of degree 1. These are the images of the most well-known curves and studied curves for which we know more or less the solution to the problem of finding the probability density function of the heating time of those curves. It's okay? Any questions?
It's okay.
Okay. So here is an example of how these curves change when you vary beta here. We take S1 beta, S superscript parenthesis 1 beta is the same as S1 beta. I simplified notations, but I could not change it here because I had this image in a file, and well, sorry for that. But so as beta vary, you see that the curve changes by having a slope more towards up or down as beta varies. Okay, so for understanding the transformation S alpha beta, we define a new transformation sigma on our space A infinity. A infinity is union over all the A's and B's of A, B, and A, capital A, curly A, B is the set of all functions in C, 0A, R plus, such that tau of FA equals B, where tau is the integral from 0 to t of ds divided by phi squared. And this involves as well rho, which is the inverse of the mapping t tau t. Tau t is for all phi in this space, tau t is strictly increasing, yeah, so we can define its inverse function. And that's what we call rho. So rho here is rho of phi, actually. So sigma associates to phi 1 over phi circle rho of phi. The interesting thing about this transformation is that it's an involution, and we call this the Doob transform. So as I was saying, sigma is an involution in the sense that if you compose it with itself, it gives you the identity. And sigma is, of course, defined on A infinity. So this is defined on this functional space I specified before. And sigma maps, sigma reverses monotonicity. So if a function is increasing, then its image is decreasing. Conversely, if a function is decreasing, its image is increasing. And it reverses as well convexity and concavity. So as a result, which I will not explain here, we know that the distribution of Gaussian Ornstein-Uhlenbeck processes, Gaussian Ornstein-Uhlenbeck processes are processes defined as I gave before. These are processes that take the form phi of t times u0 plus the integral from 0 to t of phi minus 1 s dbs. So 1 phi of t is the exponential function, then this is the classical Ornstein-Beck processes. Otherwise, we call these the Gaussian Ornstein-Beck processes. They are more general than Ornstein-Beck processes. So if two Gaussian Ornstein-Beck processes with parameter functions phi and psi are such that phi and psi satisfy the Sturm-Liouville equation, which is the differential equation phi double prime equals to mu of phi, mu times phi, where mu is a random measure. So if two processes have their parameters satisfying this same equation, then their laws are related in an interesting way. More generally, if you think about the solutions of this second order linear differential equation, then whenever you have a particular solution, the set of all the solutions to the Sturm-Liouville equation will be given by phi times alpha plus beta integral from 0 to t of ds divided by phi squared s. So this for all alpha and beta in R span all the solutions to the Sturm-Liouville equation that is given above there. And now you see that from S alpha beta, we are defining now a kind of new map that is given by this function here, which is a function of phi. So we go now to defining the family pi alpha beta. So pi alpha beta is defined for alpha in R star and beta in R as to phi, we associate phi times alpha plus beta, the integral from 0 to t of ds divided by phi squared s. So so pi alpha beta leaves stable the space of solutions of the Sturm-Liouville equation I just mentioned before here. Phi double prime equals to mu phi, and this pi alpha beta has a kind of scaling property. So pi alpha beta equals to alpha pi 1 beta over alpha, and it has some nice composition property. So pi alpha, So pi alpha beta circle pi alpha prime beta prime is given by pi alpha alpha prime alpha beta prime plus beta divided by alpha prime. So this reminds us of matrix products, etc. And actually, pi alpha beta is the inverse operator of pi 1 over alpha minus beta, and pi 1 beta for all beta non-negative is actually a semigroup. So this semigroup property is intuitively is explained intuitively by the fact that if you combine the solutions to a linear differential equation, then you will find other solutions to the linear differential equation. Yeah. So from the point of view of ordinary differential equations, this semigroup property is intuitively well understood. Shall I carry on? Any questions? Yeah. Shall I carry on?
Yes.
Okay.
So
let's just go back to the transformation S alpha beta. I have introduced sigma and I introduced pi. And actually, S alpha beta is nothing but sigma convoluted with pi alpha minus beta convoluted with sigma. And so the sigma being an involution and pi alpha minus beta satisfying some kind of semigroup property and composition property, the composition property of pi alpha minus beta is inherited by S alpha beta, and S1 beta is actually a semigroup when beta varies in the non-negative real half line. Furthermore, S alpha beta satisfies some analytical properties that are given here. I do not have time to look at all these things, so I should speed up a little bit. So here is a proposition. So if mu is a random measure on R plus, then there exists a unique positive increase in concave and differentiable function f with f0 equals 1, which satisfies the nonlinear differential equation that is given here. And f double dash here is the second derivative of f in the sense of distributions. And furthermore, S alpha beta of f alpha in R plus and beta in R is a set of positive solutions to this nonlinear equation. So, remember what we said about pi alpha beta. Pi alpha beta spans the image of a solution to the Sturm-Liouville equations, spans all the solutions to that Sturm-Liouville equation. And here S alpha beta applied to a particular solution of this equation spans all the solutions to this nonlinear equation. As an example of images, if you take the random measure a1 plus bt over the power minus 2 dt, we get ft equals to kt plus 1 to the power gamma, where kappa, kappa, not k, sorry, where kappa is square root 4a plus b squared, and gamma equals 1/2 1 minus b over k. And we get that for alpha positive and beta real, the function given here solves also the above equation. And you can go further, and mostly such equations are not obvious to solve. Oh, they are not easy to solve. So as alpha beta, just to gather this in an image, is obtained by composing sigma with pi alpha minus beta and sigma. Okay, now I do not have time to go through the proofs of this, so I skip this and go to the example. So as an example, we could compute the distribution of the first time when we hit this quadratic function divided by the polynomial of degree 1 given here. So Groenboom computed the distribution of the heating time of this quadratic curve, and we can apply that to obtain the distribution. Well, we can apply the results of Groenboom to compute the PDF of the heating time of F2, which is given as here in terms of the area functions. Is there something? Sorry, I could hear a noise.
Yes, I'm sorry. I stopped the microphone of
Okay.
our colleague. Okay.
No problem. So, well, for that family of curves, we obtain explicitly here the distribution of the heating time of the image by S alpha beta of F2, which is given by this function here times this function times this sum that involves the ratios of areas function and then an exponential function where zk's are zeros of the area of function of a transformation of the area function. Okay, so this is the first part of my talk, and now I will talk for the remaining time. Hopefully, I will say what I want to say, but let me introduce the Ornstein-Uhlenbeck processes, which are defined as solutions to SDEs of the form dut equals to dbt minus kut gt. Sorry, there should be no comma here. So this comma should not be here. It's just minus kut times dt, where we assume that the starting point of u is x, and this, of course, for all t non-negative. And bt here is a standard Brownian motion started at 0, and k is a real parameter. So the solution to this equation is given by this. Now we know the solution explicitly, that e minus kt times x plus the integral from 0 to t of e to the ks dbs. So this is one of the rare SDEs where we know the solution explicitly, and this is called the classical Ornstein-Uhlenbeck process. Now, by Dambis-Dubin-Schwarz theorem, which tells us that continuous local martingales can be represented as time-changed Brownian motions, we can write this ut as e minus kt times x plus w of rt, where rt is given by this function. So if you want to express w in terms of u, then you need the inverse function of r, which is given here, and which we will need later. So this is the logarithm of 2kt plus 1 over 2k. Okay, so this now looks very simple. It's just a function, which is the exponential minus kt times some real number x, which is a starting point, plus a time-changed Brownian motion, where the clock with time-changed w is just this exponential function, or function. This is a deterministic function. Okay, so we want to do the same. So I will just simplify by taking a continuously differentiable function f here defined on 0 infinity. And we take f0 to be different from 0, and we look at the first time when the Ornstein-Uhlenbeck process hits this curve f. So an extension of Strassen result implies that the distribution of t hat f is absolutely continuous with a continuous density. And so this simplifies our notations a little bit. So similarly, as we have done for Brownian motion, I define S hat alpha beta as given here. This looks like a complicated expression where now t is not defined on the whole of r plus, but it's defined only prior to zeta alpha beta, where zeta alpha beta is given by this here. So this is the lifetime of the curve of the image by S hat alpha beta of f. Okay, this transformation, I gave it, but of course there is a way to obtain it. So this is the analog of S alpha beta for the Brownian motion. So for Ornstein-Uhlenbeck processes, you have this family which involves as well K and R and S and R, K and R, sorry, and of course alpha and beta. So this transformation appears when you look at the bridge. So if you look at the image of the Ornstein-Uhlenbeck process by S hat 1 minus 1 over R capital T, where T is a positive real number, then what you obtain is the Ornstein-Uhlenbeck bridge T between 0 and 0. This is the bridge that starts at 0 and finishes at 0. This is the standard bridge of length T associated to U. Yeah? Are you following me okay?
Yes, alhamdulillah.
So here now, here's the thing that does not work. So I would like to show you one slide. I shared the wrong thing. There. Yeah, can you see it now?
Yes, yes.
Two properties for the function transformation. I'm sorry, I struggled to compare this with the other, but seemingly DVI PS did not compile this well, and so S hat alpha beta can be obtained using lambda and S alpha beta as in this diagram. So below we have S alpha beta, which acts for a Brownian motion, and actually to square root 2 kt plus 1 f of st, we obtain by applying S alpha beta this image here, and we define lambda by mapping f to this square root 2 kt plus 1 f of st, and lambda minus 1 maps f to e minus kt f of rt. So actually, S hat alpha beta is lambda composed with S alpha beta composed with lambda minus 1. Yeah. Where R and S of T are as given before. So let me go back to no, I lost the other 5.
You stop sharing your slides.
Yeah, I'm having problems finding the other file now. Okay, sorry. It takes a couple of minutes before I get back where I was, so I have to highlight it like this so that I recognize the red color. Okay, so we were there. So S hat alpha beta can also be constructed using another involution, which I call sigma hat. And sigma hat is given by lambda minus 1 sigma lambda, which is also the image of f by sigma hat is also can also be written as given here. Pi alpha beta is the same pi alpha beta as we had for Brownian motion. It's not changing. The sigma hat here is again an involution. That's no surprise because we have we start with an involution. We apply sigma and then we apply sigma minus 1 to the left. So S hat alpha beta inherits the semigroup, the composition property that we had for S alpha beta, and the semigroup property for S hat 1 beta. I hear some. Does somebody have a question? No?
No questions.
Please ask questions if you have any.
Okay.
Okay, so similarly to a Brownian motion, where we looked at the Sturm-Liouville equation, now we can define this nonlinear differential equation, and sigma hat actually acts naturally on the space of solutions of this equation, and it maps actually the Sturm-Liouville equation to this nonlinear second-order differential equation. and S hat of alpha beta of F spans the set of solutions to this equation once curly F is a particular solution to this equation. Okay, so let me continue. Now I state the boundary crossing identity for Ornstein-Uhlenbeck processes. So this is the analog of the relationship we had for Brownian motions. So if we write, remember we said that the distribution of the heating time of F, when this F is continuously differentiable on the positive real half line with F0 different from 0, the distribution of the heating time of F is absolutely continuous with a PDF probability density function, which we call PF of T. With this being defined, so now we have the relationship between the PDF of the heating time of S hat alpha beta F by the Ornstein-Uhlenbeck process and the distribution of the heating time, or the PDF of the heating time of F by the Ornstein-Uhlenbeck process. So this is a very similar formula to the one we stated for Brownian motion. However, this holds for all K. This holds for Ornstein-Uhlenbeck processes. So we have several proofs of this result, which we proved with our PhD student Arya Ahari and our colleague Massimiliano Tamburino. And the simplest way to prove this result is, of course, by using the analog for Brownian motion, which involves S alpha beta. You can map from Ornstein-Uhlenbeck processes to Brownian motion, then map and then do what you want for Brownian motion, then map back to the Ornstein-Uhlenbeck processes. So that's one way to prove this. However, there are other methods, including a Lie symmetry method, as discussed in our paper with Patti, and the paper by Morave in 2020, which treats boundary crossing transformations for diffusion processes. So the result we found here is somewhat hidden there in his calculations. But I will not talk here about the Lie symmetries approach, and those interested can find the methods well explained in our papers. So as an example, we look at how constant thresholds or barriers are transformed by this transformation. In other words, we know the distribution of the heating time of a constant by an Ornstein-Uhlenbeck process, and the question is, how is this constant transformed by S hat alpha beta, which I gave before? S hat alpha beta is given here. And so the second question is how to obtain or what do we obtain as PDFs of the distribution of the heating time of the images of this constant by S hat alpha beta. So the distribution of the heating time of a constant by Ornstein-Uhlenbeck processes is well studied in literature, and papers one could find include our survey, which appeared in 2005 with Patty and Pedersen. And so if we again define the PDF of the heating time when start from 0 of A, of a constant A, then this PDF, the PDF of the heating time of A by the Ornstein-Uhlenbeck process of parameter minus K is given by this function here times the sum given here, where d nu is the parabolic cylinder function with index nu, and the nu jb is the ordered sequence of positive zeros of the parabolic cylinder function d nu of b. And d nu g minus a square root t of 0 is given by this expression here. While d prime, this derivative here, is given by the partial derivative with respect to nu, with respect to the index of d nu b taken on nu equals to nu jb. Now, this is a complicated expression, but it's explicit. In particular, you can use this to simulate the function, the PDF of this, of the heating time of A by an Ornstein-Uhlenbeck process. Okay, so the image of a constant by S hat alpha beta is obtained here. So it's A e minus kt divided by square root 2k alpha times the square root of the product of these two functions, which involve alpha beta e to the 2kt minus alpha beta plus 2k, and then here, so it's a combination of k and e to the 2kt for the first term, and the combination of k, k e to the 2kt, e 2kt, and minus k for the second term. So it's a little bit complicated. However, if you set alpha beta equals to 2k, then this simplifies to this curve here, or this family of curves, which looks quite simple. And our identity, boundary crossing identities gives us this expression for the PDF of the heating time of S hat alpha beta of A by the Ornstein-Uhlenbeck process. So I should mention that Breeman and Shep have linked the distribution of the heating time of a constant by an Ornstein-Uhlenbeck process to the distribution of the first heating time of a square root boundary by a Brownian motion, which could explain why we are having here a kind of square root boundary. So their work is kind of seminal, and it was much appreciated since then. We did not know much about heating times of Ornstein-Uhlenbeck processes of constant levels. And also, I think originally that's their work that inspired our original paper with Pierre Paty, so I could not give a presentation on this without mentioning these two names. As I said, so there is a paper with Ahari, myself, and Tomborino on boundary crossing problems and functional transformation for Ornstein-Uhlenbeck processes, which you can find in the web, in archive. And there is the previous paper with Pierre Paty, including the one that appeared in the proceeding of the American Mathematics Society in 2014. That's the one I was referring to a lot in the paper. I also included some references I mentioned, including the Dimitri's paper on Lee symmetries methods in boundary crossing problems for diffusion processes, which appeared in ACTA Apple Math in 2020. I think this is all what I wanted to say. Thank you for your attention.
Thank you, Larbi. Thank you for this very nice talk. Then, please, colleagues, do you have any question?
Assalamu alaikum.
Yeah.
Can I say something?
Yes, of course.
Assalamu alaikum. Eid Mubarak. Eid Mubarak to all. Thank you very much. Thank you, Professor, for a nice talk. It's very advanced, mashallah. And I worked on some of these, not necessarily transformations, but using the Brownian motion with drift on platelet distributions inside the blood vessels in the early 90s. And I worked on few papers in this regard, but your work is since it's 30 years ago. It's very advanced, mashallah. I've included a couple of references in the chat. It's for the new researchers, etc. Honestly, it's marvelous work, and alhamdulillah, these transformations that you've presented lead to a lot of applications, especially that there are many connections between kind of the Fokker-Planck equations, the Kolmogorov type of settings, the transformations that connections between partial differential equations and stochastic processes, etc. It's a lot of research in this area, and even connections with Navier-Stokes equations. So this triangle type of research should be investigated further for the new researchers, the younger ones. I'll be happy to provide any support for anyone in this area. It's one of my favorite areas. And basically, congratulations on your papers and your presentations. And we look forward to seeing more of this kind, inshallah.
Thank you very much, Fatih.
Thank you. Most welcome, Habib.
Thank you also for the links. I think I will ask Wissam to forward them to me, please, because I'm not sure whether I will find the path to come back here.
Yeah.
So,
one of them is the Fokker-Planck equation by H. Riskin, and the other one is the other one is by Gardner, the Handbook of Stochastic Methods. And I advise these to anybody that is starting to look for to research in this area, because these are like the Bibles of this area, and they're like basically from the 80s, these books, and even before. So,
yeah.
But they present the rudimentary areas about the differences between the Ito and Stratonovich calculi, and even they allude to maybe the Malavian type of calculus in this area, stochastic calculus. And the different points of views, because maybe, if I may, say a couple of words in this area. The type of this is the Lagrangian point of view of, like, basically if you have particles. Let's say you are teaching students. There is a difference between when you have 500 people for a basic course in an auditorium versus when you have, let's say, 3 or 4 graduate students that you are following for their PhDs or master's degrees, etc. Each student in the auditorium that you have 500, for example, you have a population there. Each one has what you call a path, or you have a type of function, or a stochastic equation by himself for one particle. And also the same for the graduate students, So for the 500, you are likely to want to change from the Lagrangian point of view, where you are following each particle, because you have too many, and you say you have a population, to a more Eulerian approach, where you have the differential equation. So you look for distribution, you look for PDFs, you look for kind of a probabilistic point of view of like you have 20% that are passing, you have like, you know, and you have like say 10% that are failing, etc. So you look for this type of view where you have like the Eulerian point of view. While if you have, let's say, 3 or 4 PhD students or whatever, then you are likely to stay on the Lagrangian point of view because each one of them is very important, like, you know, in terms of we are following from for 4 or 5 years. This is just, you know, one application whereby we can distinguish between what is labeled as Lagrangian point of view versus the Eulerian point of view. These transformations that you have done only can only basically connect more with this type of duality that we have between these two types of points of views, and God knows best.
Thank you for your comments. It sounds very interesting. I will think about it.
Alhamdulillah. Shukran.
Shukran jazilan.
Shukran.
Thank you. Are there any other questions, please?
Just a remark. Please, can you go to slide 16, Larbi, please?
Page 15.
16. 16.
Yeah, I will go there.
Just a remark, maybe a remark. Yeah. 16.
16, right?
Yes. This is 17. Before. 18. Okay.
15?
No. 16. Okay. Sorry, 26, maybe 26. I forget exactly the 26 maybe.
Let's go slowly.
Okay.
Is this one?
No, not this one. Okay, no problem.
The one
I
before
forget.
is where I switched to the other file, right?
Where you define WRT, the Brownian motion. You have some Brownian motion.
That is there. That is there. That's later, is it? Before sigma hat, that's here, right?
Yes, exactly. RT, the index RT must be positive or not?
Yes, it is, because K is...
yes, non-negative, yes. Sorry.
Otherwise, we need to...
Yes, it's okay.
It's okay, even if K is negative, because then you multiply by minus, is it?
Mm-hmm.
For all K, this is fine.
Yes, this is fine, yes. RT
it's troubling to see it like this, but in the end, that is what's there.
Okay, thank you.
But you are right. If K is negative, then S of T is not defined on the whole of RT.
Okay.
You need to stop it wherever is appropriate, right?
Mm-hmm. Right. Thank you for your nice talk.
Thank you very much for your question and for your comment.
Okay. Are there any other questions, please? I have a question for you, Larbi. Could you please go to maybe slide number 10?
Slide 10.
10, yes.
Yeah.
9, maybe. Okay, because you sent me a slide. Okay, the section on Brownian motion and the square root boundary. The section functional approach. Sorry. Maybe it's above. Yes, once more, please. No, yes, 7. Okay.
I'm not sure. Did we look at the square root boundary? What do you?
Okay, then what I have in front of me is different.
What do you mean? You mean maybe later at the end, right?
Yeah, an equation in which the parabolic cylinder function is involved.
Yeah, that's later. That is here.
That's at the end.
Yeah. And
29.
yeah. You're right. You're right. You're right.
Yeah, Ernestina Lembeck.
Okay. Then,
What do you mean, right?
Just keep the one before, 29. Then for you it will be 29 maybe.
Yeah.
This one.
All
Could
right.
you please just don't move? Then P0 of t is a PDF, huh?
Yeah.
Okay. Would you allow me to share something now, just to compare?
Yeah. Please do, if you can.
If Nabil allows me.
But P0A is known, right? So
You can, but Larbi must stop the sharing.
will I stop sharing?
Yes.
Okay.
And you
I
can
just
listen.
want to.
Now you
I
can
just
share
want
maybe.
to compare something very funny. Okay.
We do not see what you are sharing. Maybe it's coming.